All right, so today we're going to be talking about inequalities. It's our second algebra lecture. So often in algebra, we think about equations, equalities, and then how to solve those. But there's a whole other section of algebra that's about inequalities, right? And inequalities show up pretty often, I'd say. Although definitely not as often as maybe other topics, but inequalities we show up very often, and in this handout, we'll talk about the basics about solving inequalities. And we'll show you four of the most common inequalities used in proofs and problem solving. So the trivial inequality, the AMGM inequality, the triangle inequality, and the Cauchy-Schwarz inequality. And there's definitely more famous inequalities in mathematics. So for example, like Jensen's inequality or T-U's lemma. These four are some of the most well-known inequalities. And other than these inequalities, uh, one should also be well-versed in algebraically manipulating regular inequalities. But we assume that that is something that everyone can learn or has already learned. So we'll start off by presenting the four inequalities in order. So the trivial inequality says that for all real numbers, x, x squared is greater than or equal to 0, and equality holds if and only if x is equal to 0. So this is pretty basic. It just basically just says the square of any real number is non-negative, and it's only equal to 0 if x itself is 0. And you can see that because it's so simple and easy to understand. That's why it's called the trivial inequality. And when you get to a level that you're writing proofs, this statement itself does not need proof. Okay. Right. AMGM inequality. So the AMGM inequality says that the arithmetic mean AM of a set is greater than or equal to the geometric mean or GM of the same set of numbers. So algebraically, it is expressed as follows. So for a set of non-negative real numbers, a sub 1 through a sub n, the following always holds. The sum of all of the a sub I over n is greater than or equal to the nth root of the product of a sub 1 through a sub n. And below there is a shorthand notation for the same inequality. One important thing to note is that this holds for non-negative real numbers and not all real numbers. And next, we also have that the equality condition of this inequality states that the arithmetic mean and geometric mean are equal if and only if all members of the set are equal. So the left-hand side, the arithmetic mean is always greater than or equal to the right-hand side, but it's only equal when all the members are equal to each other. All right. Next, we have the triangle inequality. Now this is sort of geo-related, but we can also count it as inequality. So that's why we included it in this lecture. So the well-known form of the triangle inequality is that the sum of the two shorter sides of the triangle must exceed the length of the longest side of the triangle. And it is expressed algebraically as follows. So in a non-degenerate triangle ABC, you have that AB plus BC is greater than AC, BC plus AC is greater than AB, so on and so forth. There's also a way to express this using absolute values and differences between numbers, but we will not be getting into that for this lecture. And in degenerate triangles, so a degenerate triangle is basically a triangle that's like a straight line. The strict inequality must be replaced with greater than or equal to. The triangle inequality can also be extended to other polygons. So if the lengths of an n-gon, a sub 1 through a sub n of a non-degenerate n-gon, sorry, it's only possible if, well, in shorter terms, basically, in every polygon, each side must be smaller than the semiperimeter. You don't really have to worry about the notation in the middle too much, but essentially, you just cannot have a single side that's greater than the sum of all the other lengths. Oh, and if it is equal, that would make it degenerate. And if it is, otherwise it has to be less than the semi-perimeter, which is half of the perimeter. All right. And now we have the last one, and it's the most, I'd say, algebraically complicated one of the four that we present today. So the Cauchy-Schwarz inequality, you can read about the history up here. But there are three forms of this inequality. There's the elementary form, the complex form, and the general form. For this lecture, we'll only be discussing the elementary form and the complex form. You guys do not have to worry about the general form as of now. So the elementary form of the Cauchy-Schwarz inequality states that for any real numbers a sub 1 through a sub n and b sub 1 through b sub n, we have that the sum of the products of a sub I and b sub I squared is less than or equal to the sum of the squares of each individual term in a sub 1 through a sub n multiplied by the sum of each individual term squared from b sub 1 through b sub n. And equality holds if and only if there is a non-zero constant mu such that for all a sub I, b sub I can be obtained by multiplying this constant value by with the a sub I. So as it is written here, basically you can scale down the sequence a sub 1 through a sub n, or scale up or scale down, doesn't matter. You just have to scale it, and you can obtain the sequence b sub 1 through b sub n by simply multiplying a sub n by a sub 1 through a sub n by a scale factor. And next we have the complex form, which is basically different from the elementary form in the sense that we are discussing complex numbers. And in this case, then we have that the magnitude of the sum of the products squared is less than or equal to the magnitude of each individual term squared from each sequence and then multiplied together. And we don't have to worry about where it follows from for now, but just understand that the Cauchy-Schwarz inequality can be applied to complex numbers as well. But rather than comparing, it's hard to compare two complex numbers, but when you compare the magnitudes, then Cauchy-Schwarz can apply to these complex numbers as well. All right, so I did a lot of talking about these four inequalities, but we should work through some examples to see how this is applied in real problems, right? So the first one, this first one actually does not require any of the inequalities I just taught. Rather, it just involves interpreting a problem, writing an equality, and simply knowing how to algebraically solve a simple equality. So there's no need for like to apply any of the four main inequalities before. This is just like a warm-up problem, because not all inequality problems will require those four, but oftentimes those four inequalities can help greatly simplify a problem or is even required to solve the problem. All right, so here we have a tennis player computes her win ratio by dividing the number of matches she has won by the total number of matches she has played. At the start of a weekend, her win ratio exactly 0.500. During this weekend, she plays 4 matches, winning 3 and losing 1. At the end of the weekend, her win ratio is greater than 0.503. What is the largest number of matches she could have won before the weekend began? So the first thing about solving these very wordy problems is just putting it into an equation or an inequality. Right, so if we got what we want, so let's call the number of matches she could have won before the weekend began n, right? Then at the start of the weekend, her win ratio is exactly 0.500. That means she's won half of her matches, which means she's played, if she's won end games before the weekend began, that means she's also played 2 end games, right? Because 1 over 2 is equal to 0.500. And then she says, after playing 4 matches, winning 3 and losing 1, her win ratio is greater than 0.503. So if she wins 3 matches, the numerator increases by 3, and since she played 4 matches, the denominator increases by 4, right? Because the numerator is the total number of wins she has, and the denominator is the total number of matches she has played, right? So this n plus 3 over 2n plus 4 is greater than 503 over 1000, right? Because we don't want to work with a decimal right now. We want to work with a fraction. And when you're faced with something like this, you can simply cross multiply, right? So basically what happens is you multiply the numerator of the left fraction with the denominator of the right fraction, and the numerator of the right fraction with the denominator of the left fraction, right? So I'll circle the pairs. This pair, this pair, this pair, and this pair, right? And then from here you get that 1000 times n plus 3 is greater than 503 times 2n plus 4. Then we get 1000 n plus 3000 is greater than 1006n plus 2012. And so n is 6n is less than 988, and we have n is less than 988 over 6, which is equal to 164 and 2/3. And since n represents the total number of matches that she could have won before the weekend began, it has to be a whole number. So therefore our answer, if n is the greatest number less than 164 and 2/3, the greatest whole number less than 164 and 2/3, n is necessarily equal to 164, and we have our answer. And because today I have Adrea here helping me, if you guys have any questions, then feel free to ask Adrea in the chat. He can help answer your questions if I am busy lecturing and do not notice your question. Also, if you don't feel like typing, you can also speak up, but some people are too shy to do that, so it's fine to use the chat as well. All right, so let's do the next example. For this example, we say for non-negative real numbers a sub 1 through a sub n, show that if the product of a sub 1 through a sub n is equal to 1, then the sum of these numbers is greater than or equal to n. Well, here we have the product, and here we have the sum, right? So this gives us a hint to use AMGM, right? So if we recall what AMGM says the sum of the arithmetic mean is always greater than or equal to the geometric mean, right? So that means the nth root of a1 an is less than or equal to the arithmetic mean, right? But then we notice that if we plug in the fact that the product of all these numbers are 1, then that just means that the sum is greater than 1, right? And then if we multiply both sides by n, then n is clearly non-negative, or n is clearly positive, right? So we don't have to flip the sign. And then we have a sub 1 plus a sub n is greater than or equal to n. And we notice that's exactly what the problem wanted us to do, right? So we're done with this problem. And here we just see a very basic example of the application of the AMGM inequality. Right, here we have a more indirect application. So we have find the maximum of 2 minus a minus 1 over 2a for all positive a. Now we can rewrite this expression as 2 minus a plus 1 over 2a. And to maximize this expression, 2 is a constant, right? So what we want is the minimum of this expression, right? And we can do this via AMGM. We know that a plus 1 over 2a over 2, the arithmetic mean of these two numbers, is greater than or equal to the geometric mean of these numbers, which would be root 2 over 2, right? So that means that the minimum value of a plus 1 over 2a, sorry, that looks not like an a plus 1 over 2a, the minimum value of that would just be, well, it's greater than or equal to root 2, right? So that means the minimum value of it would be root 2. And if we plug this value back into our original expression up here, then we can see up here, then we can clearly see that the maximum value that this can attain is 2 minus the square root of 2. And so often you'll see that when using AMGM, you can have like a number and then some fraction over that, or rather a variable, and then some number over that same variable. And if it asks you to maximize or minimize, then you should know that maybe you can use AMGM to combine these two expressions. Because remember that when you take the geometric mean, you are multiplying those two things together. And that means that the variable and the other number that has the variable in the denominator will have the variable cancel out, right? Which would be good towards your calculations. So yeah, that's another example of AMGM. Okay. Here we have another example of AMGM. So we have prove that a squared plus b squared plus c squared is greater than or equal to ab plus bc plus ca, and a to the fourth plus b to the fourth plus c to the fourth is greater than or equal to a squared bc plus b squared ca plus c squared ab. Now, both of these borrow from the same concept, but let's do the first one first. Also, this problem is sourced from one of Evan Chen's handouts on Olympiad inequalities. And when you if you are interested in learning more advanced math, or progress to a higher level that we can teach you, then you can probably check out Evan Chen's handouts that have more difficult concepts and also way more difficult problems. All right, so let's do the first part, right? So prove that, we'll do the other part on the other side, right? So first, let's prove that a squared plus b squared plus c squared is greater than or equal to ab plus bc plus ca. Right, so let's do AMGM, right? And you might ask, well, how do we do AMGM, right? Because if we take the arithmetic mean of like the left side here, we do not get the right side when we did, right? So you might ask, how do we do that? Well, let's group the terms into pairs instead, right? Because when we take the square root of a square, we get, well, a whole number, or rather a whole variable. But let's see how that would look. So first we have a squared plus b squared over 2 is greater than or equal to the square root of a squared times b squared, which would just be ab, right? And then we have b squared plus c squared over 2 is greater than or equal to bc, right? And then we also have that a squared plus c squared over 2 is greater than or equal to ac. And then you might notice, wait a minute, like AB is on the right hand of this expression, right? BC is also in the right hand side of this expression. And AC is also on the right-hand side of this expression. And now you notice that if you take these three equations, right? That is, okay, wait. Sorry. If you take these three equations and you add them together, then what you would essentially get is this inequality here. So let me just write that out for you guys. Because if you have a squared over 2 appears once in the first inequality, let's number these. Hold up. 1, 2, and 3, right? So a squared over 2 appears in inequality 1 and inequality 3. So that means a squared will appear in the sum. And then if you iterate through this process, you will see that adding together these three inequalities, and you notice the sign is the same in all three of them, we would get that a squared plus b squared plus c squared is greater than or equal to ab plus ac plus bc. Right, so that's the first inequality down. Now the second inequality has a similar way of solving, but rather than simply grouping into pairs, we want to figure out a way to decompose the groupings such that there is a more reasonable way to create the right hand side of the expression. And what we can do is, because they're raised to the fourth power, we want to think about breaking them into group sets of 4, right? So how we would do that is as follows. We have a to the fourth over 4, a to the fourth over 4, b to the fourth over 4, and c to the fourth over 4. And I'll show you how this works as follows. So if you have So if I bring my screen over here, we have that a to the fourth plus a to the fourth plus b to the fourth plus c to the fourth all over 4 is greater than or equal to the fourth root of a to the fourth times a to the fourth times b to the fourth times c to the fourth. And this is just equal to a squared bc. Now you might already see where this is going, right? Because a squared bc here, right? But then we also have a squared bc here, right? And we can do the same thing, right? So if we have b to the fourth plus b to the fourth plus a to the fourth plus c to the fourth over 4, that's greater than or equal to b squared ac. And similarly, we will have c to the fourth plus c to the fourth plus a to the fourth plus b to the fourth over 4 is greater than or equal to the geometric mean of these 4 numbers, which would be c squared ab, right? And now we can do essentially the same thing as before, right? If we add these 3 inequalities together, we would get the same thing as we would here, right? I won't bother writing it here, but the general gist, as you can see, is that we broke down this seemingly hard to prove inequality, and then we used AMGM onto these broken down parts, and we managed to come up with a solution to this seemingly complex inequality just by using AMGM. And you'll see that sometimes AMGM doesn't present itself to you quite obviously in the problem, right? But by breaking or by manipulating the expressions, and then you can get something that you can use AMGM on, and then you can solve the problem quite easily from there. All right, let's do another example then. And this example, we'll touch on the triangle inequality. So far we've used AMGM, we've used basic inequality manipulation, and now let's do one with the triangle inequality. So here we have the lengths of the sides of a triangle with positive area So if it says with positive area, that means that it's non-degenerate. Okay. A degenerate triangle can have no area, or a degenerate triangle has no area, more specifically. And then it says find the number of possible values for n. So we just apply the triangle inequality. So clearly the longest side of this triangle is going to be either log base 10 of 75 or log base 10 of n, right? If n is greater than 75. Right, so first we have the log base 10 of 12. Let's consider the first case that n is less than or equal to 75, right? So first we have log base 10 of 12 plus log base 10 of n. 10 of n is greater than log base 10 of 75, right? And in this case, if we use the property of logarithms, we have that the log base 10 of 12n is greater than the log base 10 of 75, right? And here we just use the property of adding logarithms. Then we know that n is greater than 75 over 12, which is 6.25, right? That's not equal to 6.25, right? Next, we want to consider the other case. So the other case here, we have that n is greater than 75, right? And here we would have log base 10 of n 12 plus log base 10 of 12 plus the log base 10 of 75 would be greater than log base 10 of n. And notice that we used strict inequalities, so strictly greater than and not greater than or equal to, because if we go back to the problem, it said positive area, and for non-degenerates, it's a strictly greater than or greater than sign, or strictly less than sign, depending on how you manipulate the inequality. So if we continue using the property of logarithms, we have log base 10 of 900 is greater than the log base 10 of n, which means that n is less than 900. So if we combine these two intervals, then we have that n is between 6.25 and 900, exclusive, meaning that 900 is not included and neither 6.25. And we want to find the number of possible values for n, and n is a positive integer. So that means n is any number between any integer between 6.25 and 900 exclusive, and the number of positive integer n which satisfy this requirement would be 893. And you can find this either by finding the total number of, you can find this by finding the number of integers between 6 and 900 exclusive, and you would do that just by doing 900 minus 6 minus 1, and that would be the total number of integers between 6 and 900 exclusive. All right, so that was an example using the triangle inequality, and for this problem you would also have to know some basic properties of logarithms. All right. All right, so here we have a harder problem. Let x and y and z be positive reals. I want to show that x plus y plus z multiplied by the quantity 1 over x plus 1 over y plus 1 over z is greater than or equal to 9. And this problem can be solved two ways. So the first time that we solve this problem, we want to use the AMGM inequality. And for the second time that we solve this problem, we want to do it using Cauchy-Schwarz. Right. All right, so let's split the screen into two sections. One section here will be AMGM, let's do AMGM. Let's do AMGM first. Right. AMG. Authority, did you have something to add?
Oh yeah, after you do the AMGM, I'll add it.
Which one?
No. For this problem, after you okay, after you go over the AMGM, I'll just quickly say something.
Okay, sure. Okay, so we have that we want to show that x plus y plus z plus times 1 over x times 1 over y plus 1 over z is greater than or equal to 9. So we can do this as follows. So we have that x plus y plus z over 3 is greater than or equal to the third root of xyz, clearly. And then we also have that 1 over x plus 1 over y, oops, did not mean to put a parenthesis there, plus 1 over z is greater than or equal to the third root of 1 over xyz, which is also equivalent to 1 over the cube root of xyz, because we can do like the third cube root of 1 over the cube root of xyz, right? And if we multiply these two, oops, I forgot the over 3 here. If we multiply these two expressions together, we would get that, oops, x plus y plus z over 3 multiplied by 1 over x plus 1 over y plus 1 over z over 3 is greater than or equal to, well, if we multiply the third triple, the cube root of xyz with the 1 over the cube root of xyz, we would have that this would be 1, right? And we recall that both of these inequalities are positive, right? Because we have the restriction that x, y, and z were positive real numbers in the problem itself, right? In the first sentence. So now, as you can see, if we multiply both sides of this inequality by 9, we would have that x plus y plus z times 1 over x plus 1 over y plus 1 over z would be greater than or equal to 9. Okay. And so as you can see, solving it with AMGM was relatively easy. You had two, I guess, factors that you were multiplying together. And if you applied AMGM separately to those two, I guess, sequences, you could call them, and then you combine those results, you would get the desired inequality. So now let's solve it using Cauchy-Schwarz, right? So Cauchy-Schwarz with this is a little bit more, it's even faster actually, I would say. So let's write down what it would look like for 3 variables first, right? Because Cauchy-Schwarz, I would say, is the most difficult inequality to understand. So the Cauchy-Schwarz inequality for 3 variables would be that a sub 1 squared plus a sub 2 squared plus a sub 3 squared, right? I'll use a different color for the second sequence, times b sub 1 squared times plus b sub 2 squared plus b sub 3 squared is greater than or equal to a sub 1 b sub 1 plus a sub 2 b sub 2 plus a sub 3 b sub 3 squared. Now what we can do, if we let a sub 1 equal root x, b sub 1 equal 1 over root x, and so on and so forth for y and z for a sub 2 and b sub 2. So a sub 2 would be root y, b sub 2 would be 1 over root y, and then a sub 3 would be root z, and then b sub 3 would be 1 over root z. And you'll notice that if we plug them into this above expression here, the left-hand side of the above expression, we would have x plus y plus z times 1 over x plus 1 over y plus 1 over z. Now, the right-hand side would evaluate to, right? The right-hand side would evaluate to 1, right? Because root x times 1 over root x is 1 plus 1. So because root y times 1 over root y is 1. And then 1 again, because root z times 1 over root z is 1. So that would be greater than 1 plus 1 plus 1 squared, which is equal to 9, right? And the left-hand side, as I mentioned before, would evaluate to this left-hand side here. Hold on.
Oh yeah. To quickly add actually to the AMGM method, like another way that you could have thought about using the AMGM method is just by expanding the left-hand side. So when you expand, you get like 1 plus x over y plus x over z plus y over x plus 1 plus y over z and so on. And then if you go back to example 2.2, you can just plug in those numbers into example 2.2 and you get the exact same inequality. Yeah, so like if you let a1 equal 1 and then a2 let equal x over y and then a3 equal x over z and so on, then they do in fact multiply to 1. And if you sum them, they must be greater than or equal to 9 because there's 9 terms in the product.
Mm-hmm.
Yeah.
Yeah, so you could either do them without expanding or expand and then do AMGM. Personally, I would prefer doing AMGM first because expanding it is like an extra step in a way, but you can also expand it and do AMGM. All right, so here we can see that this inequality could be solved with both AMGM and Cauchy-Schwarz. So it was a good example to show how to use both of these inequalities in a problem. And one trend you might be noticing is that some of these problems are actually proof problems. And they're slightly more, so that means inequalities are like slightly more advanced than maybe what you would find typically. But I feel like they do show up enough in, like the AMCs and maybe even math counts that it does warrant talking about. And it'll also prepare you for proof writing in the future. Because inequalities are one of the biggest, I guess, topics of algebra that they often ask you to prove on high-level competitions such as the JMO or the AMO. All right, so let's tackle this problem. It says let A and B be positive real numbers with A plus B is equal to 1. All right, so let's remember that. A plus B is equal to 1. And let's think about how you can use this, right? So we want to prove that A squared over A plus 1 plus B squared over B plus 1 is greater than or equal to 1/3. And this problem is actually from an actual Olympiad. It's from the Hungarian Math Olympiad. So one thing that we are immediately annoyed by is the fact that these denominators have a +1 in them, which means that they're annoying to deal with. But we can see that Cauchy-Schwarz can also eliminate denominators quite easily, right? So what we would do here is we can do as follows. We have, let's do, the first set would be, let's see, we would have A plus 1 and then B plus 1. And on the other side, we would have A squared over A plus 1 plus B squared over B plus 1. So that's the original left-hand side of the expression, right? And this would be greater than or equal to, using Cauchy-Schwarz, this would be greater than or equal to, well, we would have A1 times B1. So A1 would be root A plus 1. right? And then b sub 1 would be the square root of a squared over a plus 1. So that would be a over the square root of a plus 1, right? And then we have a sub 2 times b sub 2. So a sub 2 would be the root of b plus 1. And the other one would be b over the root of b plus 1, right? That, hold up. Okay. My Wi-Fi I think glitched out for a moment there. I just wanted to make sure that it's showing up on the screen. All right, so this plus this, right? And then squared, according to Cauchy-Schwarz. And here we can see that the root a plus 1 cancels with the root a plus 1 in the denominator. We also see that the root b plus 1 cancels with the root b plus 1 in the denominator. And so what we get here is essentially a plus b, right? Squared. And we already have a plus b squared, right? They gave us a plus b squared in the problem. And we have that a plus b is equal to 1. So this is just 1, right? And then we also have that a plus 1 plus b plus 1 is equal to this here is equal to a plus b plus 2, right? So that would just equal 3. Sorry, excuse me for a second. Right. Then we would have that 3 times a squared over a plus 1 times b squared, oh, sorry, not times, plus b squared over b plus 1 is greater than or equal to 1. And then when you divide both sides, you would simply get that a squared over a plus 1 plus b squared over b plus 1, b squared over b plus 1 is greater than or equal to 1/3. So you can see that with the help of Cauchy-Schwarz, we were able to solve even an Olympiad problem in just very few steps, really. It was just one application of AMG, sorry, not one application of AMG, one application of Cauchy-Schwarz. And although this problem is very old, so I don't think modern Olympiad problems will have problems that can just be solved with one application of Cauchy-Schwarz. It still shows that Cauchy-Schwarz is really, really helpful for reducing expressions. And a very key indicator of when you might be using Cauchy-Schwarz is when there are squares in an inequality, and also when you want to get rid of annoying denominators, because you can pair them up together, as you can see here, where we canceled out the denominators here. We can see that it's very helpful for canceling out denominators as well. So when you have like annoying fractions and you've tried a lot of different methods, then you can also try Cauchy-Schwarz. And it's important to remember that not all squares immediately means Cauchy-Schwarz. But here it was a good example of where you have squares and you have annoying fractions, so you can use Cauchy-Schwarz. And I've said this before in my geometry angle chasing lecture, but you want to be making sure that you can use every piece of information that you get from the problem. So here we will notice that they said a plus b is equal to 1. So whenever you see that, you should try to think of how can I manipulate this inequality so that I can use the information that a plus b is equal to 1, right? And here we thought, oh, when we use Cauchy-Schwarz, we have a plus b on some side, and then we can use the fact that a plus b equals 1. So it's always important to find ways to use every single piece of information that's given in the problem. Okay. I have 2 more examples. Let's see if we can get through them. And if we have more time, we can maybe even do the overtime problem, or I'll introduce you to it. I don't think we will be able to solve the overtime problem in the time that we have left. All right, so here we have a question. It says, the sum of the following 7 numbers is exactly 19. A sub 1 equals 2.56, a sub 2, okay, so on and so forth, right? It is desired to replace each a sub I by an integer approximation a sub I. So 1 is less than or equal to I is less than or equal to 7, so that the sum of the a sub I is also 19. And so that m is the maximum of the errors. The maximum absolute value of the difference is as small as possible. For this minimum m, what is 100m? Now, you might be thinking, what does this problem have to do with, the inequalities and everything I talked about? Well, another big part of inequalities is optimization. And it's not always going to be like you have a fraction and you want to solve it, right? For this one, it's sometimes they have what I like to call ad hoc problems, which are just problems that require just like basic algebra knowledge or like just like good logic sense, I guess, and less so like knowing advanced inequalities like Jensen's inequality and stuff like that, right? Sometimes you just want to go back to the basics. So for this problem, we have that we notice that each a sub I is between 2 and 3, right? And then we notice that if any of the approximations, so capital A sub I, is less than 2 or more than 3, then the error associated with that term will be larger than 1. So the largest error will also be larger than 1, right? Because we just want to minimize the maximum error. So then we just want, ideally, we definitely want them to be either 2s or 3s, right? We write 19 as the sum of seven numbers, each of which is 2 or 3, right? And so how will we do that? Well, we can just solve a simple system of equations. We have 2x plus 3y equals 19. X plus y is equal to 7, right? X is the number of 2's, y is the number of, what just happened? Can you guys see my screen? Okay,
No, it's not.
okay, GG. All right. I will share my screen again. I think my application crashed. All right, it's fine. All right, so going back to what I was talking about before, we have that 2x plus 3y is 19, x plus y is 7, and x is basically the number of 2's and y is the number of 3's. Now, you can either solve this little equations or you can do guess and check, whatever, because the numbers are so small they can easily do guess and check, right? So we have 5 3's and 2 2's, right? So y equals 5, x equals 2. You can check that yourself, right? I'll just write it here for reference, right? There are 2 2's and 5 3's. And to minimize the maximum error, we notice that each of these a sub i's are also closer to 3 than they are to 2, right? So ideally, we have to match the 2's with the two smallest of the a sub i's. So our approximations are a sub 1 and a sub 2 are equal to 2, and a sub 3 through 7 is equal to 3. And we see that the maximum error would be 0.56, right? 0.61, right? Between capital A sub 2 and A sub 2. And so that means that m is equal to 0.61. And if we go back to the problem, we want 100m. So that means m equals 61, right? Because 0.61 times 100 is 61. So this is an example of a problem that doesn't really require like a basic knowledge of inequalities itself, but it's an optimization problem and it uses logic and just basic thinking. And it was also an Amy problem, which just shows that like if sometimes you just don't need to know, like, well, knowing is obviously beneficial, but sometimes like you don't want to think too complicated. Sometimes it can just be like going back to the basics, using logic, and just figuring out the answer that way. All right, let's do one last example, and I don't think we have enough time to do the hard advanced problem. All right, so this problem is from USA Math Talent Search. It says find the real numbered solution to the equation below and also demonstrate that it is unique. All right, so let's figure out a way to rearrange this equation, right? So the first thing that you might notice is that you probably want this term, right? The root x, 36 over root x paired with this 9 over root x term. And you also want this 9 over root y term paired with the root y term. And then you notice that if you multiply these two numbers together, you would get the root x and the root y, or the root y would cancel, right? So that is a pretty clear hint to use AMGM. So if we do this grouping that I said before, we would have 9 root x plus 36 over root x plus 9 over root y plus root y. Right, so if we group these two terms together and those two terms together is equal to 42. And what we can do here is we can break the problem down into two parts, right? So the first part, we want to minimize 9 root x plus 36 over root x. So if we apply AMGM, we have that 9 root x plus 36 over root x over 2 is greater than or equal to the square root of 9 times 36, right? Because the root x's cancel, and this is equal to, what is this equal to? This is equal to 12, no, 18, right? 3 times 6, yeah, 18. All right, and then on the other side, wait, is this right? To make sure this is right. Oh yeah, okay, yeah, that's right. And then we would have that, if we scroll down, we would also have that. That means that 9 over root x plus 36 over root x is greater than or equal to 36, right? Now we work on the other pair of expressions. We have that, oops, that's not what I intended. It's not what I intended to do. Right, on the other side, we have that 9 over root y plus root y, right? So we can do the same thing. 9 over root y plus root y over 2 is greater than or equal to 9, the square root of 9, which is equal to 3. So we have 9 over root y plus root y is greater than or equal to 6, right? So now if we add these two expressions together, we have that this expression here, if we just, let's call it f of x comma y, this expression here is greater than or equal to 42, right? If we add these two together. So that means that any solution to this problem is unique, right? Because 9 over root x plus 36 over root x, remember what we said about AMGM, right? AMGM, the equality condition is when the two numbers are equal to each other. So 9 over root x, to find x, we would simply set 9 root x is equal to 36 over root x, and then we get x equals 4. And similarly, we would also get that 9 over root y is equal to root y, and we get that y equals 9, right? So this is the only solution to this problem because everything else would be strictly greater than 42. And here, what I did was I paired the numbers together. The other way you can do it is you can just use the whole expression as a whole. So 9 over 9 root x plus 36 over root x plus 9 root y plus root y all over 4. And then you take the geometric mean of that. But that would mean you would have to take the fourth root, which means you would have more computation, right? So you can either group them into pairs, or you can, expand the whole thing or whatever. The entire gist here, however, is to use AMGM. And you notice that the reason that we use it is because we have two numbers that are currently being added together. But we want to prove that one, the solution is unique, which is a good sign to use inequality, because if you can prove that something is always going to be greater than or equal to, that means, and you can prove that, for example, the expression is strictly increasing or something, then you can prove that the solution that you find is unique. The second thing is that the two numbers that are being added together, they're annoying to deal with by themselves, right? You don't want to deal with root y or something over root y, but when you multiply something together, it becomes something nice, right? Like say a constant in this case. So those are two pretty big hints to use AMGM. All right, it's 7:13, so I don't think we'll be going over the hard problem. We'll end it here today. So just a quick recap. We learned the four inequalities, the trivial inequality, the AMGM, the triangle, and the Cauchy-Schwarz. You notice that I didn't use the trivial inequality in any of my examples this time around, but there is one review problem that has a solution, or one or two review problems that use trivial inequality in the review problems. And the reason I don't have a problem on the trivial inequality here is that the trivial inequality is more often used in proofs. And for example, it can be used to prove, it's used in the proof for AMGM, I'm pretty sure. Or either that or it's used in the proof for Cauchy-Schwarz. But either way, the trivial inequality is pretty useful, but it's also very intuitive. So that's why it sometimes doesn't show up in like just say basic in the more lesser and the non-proof oriented problems, I would say. But there are two review problems that use it. So if you want to do the review problems that are in the handout, then feel free to do so. A second thing would just be that our next lecture is Saturday from 10 to 11 on the 24th. Correct me if I'm wrong, but it's at 10 to 11, and the lecture will be a 3S lecture. And the handout to that will be posted a day before that. And finally, the recording to this lecture will be uploaded soon after this meeting, and the solutions to the previous handout are also out. The recording for the previous lecture, so lecture 4, has been slightly delayed. So we apologize for that, but it'll be up sometime within the next 2 days. So that's it. Thank you for coming, everybody. And you are free to go. If you have any questions, stay back and ask questions.